And the next speaker is Dr. Burnett from the University of Manchester, please.
Hi everyone. Thanks very much, very happy to be here. Today I wanted to talk to you about our work in environmentally assisted cracking of 7000 series aluminium. And I just wanted to give a very brief conversion course for people that may be working in steels and other materials. But for aluminium, we essentially cannot charge it in a hydrogen gas. We have to use an electrochemical method. But it's sufficient to use just humid air for 7000 series aluminium to create that effect of hydrogen charging. So I'll get straight on. This is work in collaboration with Airbus. And just to introduce again, we've got this combination of the applied stress, a susceptible microstructure, and the environment. But the time is also a crucial aspect of this. We have to consider how long we've got available for things to happen in these different processes. So these materials used widely in aerospace have been used now in these new generation alloys, which have got a higher strength and high toughness, very clean alloys, but have shown to be highly susceptible to environmentally induced cracking in humid air. And the sort of story goes that the previous generation of materials like 7050 here have shown in this VK plot essentially a very high threshold, so a very high stress intensity factor needed to start cracking in these materials. This is all in humid air, 70 degrees and 85% relative humidity. And then when you actually reach what we refer to as a plateau, so the sort of maximum velocity that you can get at higher stress intensity factors, we also have a much lower velocity for this previous generation 7050 alloy. But for the new generation alloys, here shown 7037, 7449 and 7085, we've got a much lower threshold, so cracking can start a much lower stress intensity factor. And then when it reaches its plateau, that velocity of the cracks is much, much higher as well. And these materials are characterized that this, like hydrogen embrittlement, it's a decohesion mechanism, is characterized by these extremely brittle intergranular fracture surfaces. And basically the prevailing trend that takes us from these previous generation materials to the current generation of materials is this changing composition, which is actually making the materials stronger, and by removing iron and silicon is actually making them tougher. But actually we've got increasing levels of zinc, and crucially an increasing level of like the zinc to magnesium ratio. So the materials that I'm going to present on today are 7449 and 7085, both in an overaged temper, and they've got a typical pancake microstructure which has been deformed through hot rolling, but not massively deformed, because the actual amount of reduction from the original casting down to the final thickness, these are very thick plates, and we've tested them all in the T4 position. And what we've done, I was very happy that my PhD student Ryan Euesden spent most of his lockdown in COVID building this in situ scanning optical microscope, which we've then put inside a humidity cabinet, and it basically scans across the surface of a standalone 4-point bend specimen. So here's our specimen. It's 15 millimeters across, and we can scan this area 15 by 25. And when we scan this region, we actually are scanning over 700 images per frame. So we have to prepare these samples carefully. They're actually polished to a 1 micron finish in a water-free environment, and then we chamfer the edges to make sure we exclude cracks coming in from the edge. Could you play this video, please? So this is the view we get. This is 700 tiled images over time, and hopefully you can see that we'll start to get some cracks. It's a bit faint, I'm afraid, but we'll watch this in situ and watch all of these cracks emerge. Can we play it one more time? Is that okay? Because you'll notice that actually the first crack to form is up here, but actually there's a crack here that joins with this one. They coalesce, and actually this is a sample of the crack that causes failure overall. And overall we have over 30 cracks in the total time of a failure of this specimen. So this is a really neat method of finding exactly where those initiation sites are. And because they're it's a high resolution, we can zoom right in to see where they start. We've defined primary cracks as those that have sort of initiated independently, And the one that is the primary crack that causes failure is the dominant crack. And then we have also secondary cracks. There's quite a population of secondary cracks which actually form in the K zone ahead of the primary cracks. And this is the data that we get out, is that you can see the crack length as a function of time, and we've tested 7449 and 7085 under 2 different loading conditions. It's worth noting that actually 75% of yield strength for 7449 is the same absolute stress level as 85% of 7085. And we can see that we get this general behaviour where we actually have some time taken to form a crack in the first place, so an incubation period. And then we've got a short period where we've got like this sort of slower growth before it eventually reaches the sort of sustained long crack behaviour. So all of these tests, again, done at 70 degrees and 50% humidity. But there's also a lot of other things going on as we watch these cracks grow. Like one event here, you can see these cracks have arrested, but that's because these 2 cracks here have coalesced and basically shielded the growth of the cracks here. But we can also see other jumps, and so there's quite a lot of interaction between these cracks as they grow on the sample. But in sort of like a summary sort of behaviour, what we have is we have, for all of these systems, we have an incubation time, so a time when we don't really observe anything happening, but something is happening because it's reacting to the environment that it's in. And then we have a short crack regime, which is characterised by a quite slow and erratic behaviour. And then we have a period where it reaches a much more consistent, higher velocity of cracking. It's worth noting, we've seen that for all of the tests under different conditions that we've done, 7449 is much faster to incubate and is faster to crack. But actually, when we test at the absolute stress levels that are the same, we actually see similar behavior between the 2 alloys. So watch these 3 sites, because this is when we zoom right into the image, because it's a very high resolution image made out of like all of these tiles, and we can actually see that exact point of initiation of these cracks. And it's interesting that actually that point of initiation, if we now look again, is actually this feature here, which is right next to some very large features, and it's really not where you might have guessed the crack would have started. But because we've got these in situ images, we can actually tell that the crack starts at exactly this point. And we can find that on the fracture surface in the SEM and see that it's actually like a small gas pore cluster associated here with an Mg2Si particle in this 7449 sample. And it's quite surprising because this is such a small feature. You see each of these pores is less than 10 microns in size, and so is the particle, but also that it's not the biggest feature in the sort of local neighborhood. But we can identify this exact initiation site, and we've done this now for like numerous different sites and the different materials. So here's 2 examples of that. So we wait for the sample to crack open, so it fails naturally if we just leave the test to continue. And then we can go in, and with that knowledge of what's happened on the top surface, we can find these initiation sites. So here in this example of 7449 and here for 7085, we see a consistent trend, which these gas pores in the material seem extremely important for preferred initiation sites in this environment. We can see also that in Mg2Si is really important for these initiation sites in the 7449 material as well. But really, we're creating these clusters are really creating sort of quite vulnerable metal ligaments in the metal to form these initiation sites. But with that knowledge now, we can look a bit closer. So what we've been doing is doing very low energy EDX mapping of the surface. And this is something that you could do and easily miss it if you weren't confident that you were looking in the right place. But using 2 kV mapping of the surface, we can now see these crack arrest markings around that initiation site. So it gives us even further confidence that we found exactly the right place. But we can also see some elevated oxidation at some locations, again, which coincide directly with those initiation sites. So we've really got good evidence that actually there's water at that initial initiation site, but actually that is retained for some small periods during the short crack growth, but later on in the crack has disappeared, and we only see oxidation of the surface, and we don't see any more evidence of crack arrest markings and this elevated oxygen signal. So just to highlight these regions, we've got this, as I've sort of just illustrated here in the 7085 sample, we've got a region of elevated oxidation, which is really almost the exact point of initiation in the material between this like cluster of pores, creating a very highly stressed, localized region for initiation. And then we've got this region extending up to about 50 microns in total, depending on the different initiation sites, where we have these crack arrest markings across the surface. So just now I'm going to sort of try and pull together the sort of the mechanical information that we've got and, well, the observations of the cracks with what we've seen in the microstructure of the material. And one of the first things that we can see is that we have a sort of a consistently different behavior between the short cracks and the long cracks. So now plotting the crack velocity as a function of crack length, we see what I've plotted here as a coefficient of variation, which is basically how erratic is that crack growth behavior in the short crack regime and in the long crack regime. And we see we get much more erratic behavior of the cracks. And actually our time interval for measurement is about 2 hours to take each one of those tiled arrays of images. And I think that these cracks are actually arresting intermittently, and that sort of coincides with the observations of the crack arrest markings. But it's interesting that this velocity tries to track at the highest rate for any of these cracks, but then sort of drops down, suggesting that it sort of cracks as fast as it can, but then meets an obstacle and then like drops out. And this sort of like threshold that we've put in here is about 600 microns, where we see that transition in behavior, and that corresponds almost perfectly to the average grain dimension in the longitudinal direction, which is the direction that these cracks are propagating in. So we've also taken these cracks. Here's some X-ray CT showing actually the shape of these cracks as they grow, because as they get much bigger, because it's a 4-point bend specimen, they start to grow into the depth, and actually the cracks in the depth start to like slow down considerably, but when they're smaller they grow more consistently. But we've basically just validated with some FE modelling the analytical approach of Newman and Raju that we've used here to actually measure the K across these cracks. And you can see here, as the crack grows, we see a big difference in the K that we get at the top surface where we're making our measurements and in the depth of the sample. But we're confident now that we can create these stress intensity, crack velocity versus stress intensity factor VK plots. And what we're showing on the top is the 7449 data and the 7085 at the bottom. And we've plotted it against the open symbols are the results from this 4-point bend test compared to a more traditional DCB measurements where we have got a dual cantilever bend test and a large crack. Now these large cracks in the DCB are measured through different means, but essentially it's a large crack propagating through the material across many, many grains, very large crack, and it's coming to an arrest. And it comes to an arrest at this point. What we can see when we actually have small cracks initiating at a point and growing, and actually the K going up as they grow, they're actually growing much below this threshold, because previously it was thought this threshold really here is establishing what is the minimum K needed to actually propagate these cracks. But we've got quite a different scenario when you start from a point compared to starting with this large specimen, and actually that's the case in all of the samples, that we actually see the cracking starting at very low values of K. Just plotted on the right here is the two dominant cracks for the two different tests at the two different stress levels. And again, we see that actually the dominant cracks track very much with the sort of upper bound of velocity that you can get for these samples. But that plateau, the sort of maximum velocity they reach, corresponds like almost perfectly with the data that we get from the large scale DCB tests. So just in summary of what we found putting together that sort of crack observations and the like fractography of the samples, we see that we get an incubation time where we don't see any visible changes, but what we know from the post-mortem evaluation is that we've got this corrosive attack, but at albeit at an extremely small scale, like less than 5 microns, just quite gentle oxidation, followed by something that we've had to add in here, which is actually this behavior in the short crack regime where we do see crack arrest markings, which later disappear, because we observe these crack arrest markings up to about 50 microns, but the short crack regime that we've defined based on the mechanical behavior extends up to 600 microns. So there's maybe slightly different things happening here. And then we eventually reach this sort of sustained propagation phase where we get a much more consistent growth of the cracks. So, in summary, we've built a system which has allowed us to observe the initiation and short crack and long crack growth of these of the cracks in the humid environment for the high strength aluminium alloys, and that's allowed us to go in and find that exact initiation site and then analyze that and say what are the conditions. And I think the point I'd like to make is that at each one of those stages that I've introduced, we've really got quite a distinct mechanical and environmental scenario. So we really have to consider that when we're building our models and we're thinking about what mechanisms are important for those different stages, because mechanistically they are distinct. Thanks very much.
Thank you for the nice presentation. Maybe